Here is a combined summary of the 4 pages. In the context of explainable artificial intelligence, XAI, the paper evaluates the consistency of attribution-based explanations, introducing MetaRank, an open platform for benchmarking attribution methods in the image domain. MetaRank assesses 8 attribution methods, including saliency, input circled dot operator gradient, integrated gradients, guided backpropagation, deep lift, deconvolution, LRP, and guided GradCam, using 6 renowned model architectures on 4 diverse datasets, employing both the most relevant first, MoRF, and least relevant first, LeRF, evaluation protocols. The paper reveals 3 key insights. First, evaluating attribution methods under disparate settings can yield divergent performance rankings. Second, although inconsistent across numerous cases, the performance rankings exhibit remarkable consistency across distinct checkpoints along the same training trajectory. And third, prior attempts at consistent evaluation fare no better than baselines when extended to more heterogeneous models and datasets. The authors propose MetaRank, a benchmark metric that aggregates ranking results from diverse settings to mitigate biases associated with specific configurations. This metric enables systematic comparisons among existing attribution methods and provides extensive experiment results and discussions on the status quo. The authors also review previous attribution evaluation efforts, categorizing them into expert-grounded evaluations, which rely on human judgment, and functional-grounded evaluations, which provide more objective evaluations by comparing model behavior with individual features present or absent. The paper highlights the limitations of these approaches, including subjective evaluations, inconsistent distributions between training and test data, and scalability issues. The authors identify the need for a unified theoretical framework for evaluating attribution methods and propose MetaRank as a novel evaluation benchmark to provide a comprehensive evaluation of attribution methods across multiple settings. This paper discusses the inconsistencies in evaluating attribution-based explanations in image classification tasks, proposing a standardized evaluation framework named MetaRank. The authors formalize key concepts in attribution evaluation and derive a general assessment paradigm in explainable AI, XAI. They adopt 2 common strategies for evaluating faithfulness of attribution methods. Most relevant first, MoRF, and least relevant first, LeRF, protocols. These protocols quantify the reduction in model performance after removing top or least salient pixels of the original image. The paper also provides a summary of datasets and models used in previous studies, highlighting the lack of consistency in these settings. It establishes standardized settings for the MetaRank evaluation benchmark, including 4 datasets, NWPURESISC45, Food 101, ImageNet 1K, and Places 365, and 6 widely employed convolutional neural networks, ResNet 18, ResNet 50, Inception B4, VGG19, EfficientNet_B2, and DenseNet 121. The workflow of MetaRank is illustrated in Figure 1, showing the process of generating a ranking list of attribution methods based on their faithfulness. The proposed research paper introduces a novel approach to evaluating the consistency of attribution-based explanations in deep neural networks. It presents a comprehensive benchmark, MetaRank, which aggregates ranking results from diverse test cases to mitigate biases associated with specific configurations. This approach considers multiple factors such as datasets, models, and evaluation protocols, providing a more comprehensive view of attribution methods. The authors also propose a benchmark metric named MetaRank to facilitate a more comprehensive comparison between attribution methods. This metric views each specific configuration of the model, dataset, and evaluation protocol as one test case. It aggregates the ranking results from a diverse array of test cases, thereby mitigating biases associated with specific configurations. The paper further details the calculation of the MetaRank metric, involving the probability that one competitor outperforms another and the conversion of this probability into logistic odds. The performance discrepancy is then transformed into the difference on the MetaRank metric, allowing for a standardized comparison between competitors. The evaluation of attribution-based explanations in machine learning models is crucial for understanding their consistency and reliability across various settings. This study explores the consistency of performance rankings for existing attribution methods, including LRP, integrated gradients, and guided grad-cam, across diverse evaluation settings, models, datasets, and protocols. The authors conducted extensive experiments on meta-rank, focusing on 4 pivotal questions: the consistency of attribution methods across diverse settings, the consistency of the state-of-the-art evaluation method ROAD, the superior performance of attribution methods, and the feasibility of meta-rank in evaluating substantial methods. The results suggest a pronounced weakness in the consistency at the model level, with only 2 out of 18 cases showing strong correlations. Similarly, attribution methods exhibit noticeable inconsistency in performance on different datasets, with only 5 out of 18 cases showing strong correlations at the dataset level. Figure 3 illustrates the Spearman rank correlations among several cases, highlighting the correlation among 9 test cases in MoRF and LeRF, and between MoRF and LeRF on the same 9 cases. The study also examines the inconsistencies in attribution-based explanations across different evaluation protocols and checkpoints. A detailed comparison of 8 attribution methods using 2 evaluation protocols, MoRF and LeRF, reveals significant inconsistencies, with no strong correlation observed. However, the study finds high consistency in the ranking of attribution methods across different checkpoints, with rankings tending to stabilize rapidly as the model converges. The paper highlights the necessity of the meta-rank benchmark for evaluating attribution methods, emphasizing that relying solely on ROAD is inadequate due to inconsistent correlations between rankings. A unified ranking list for the 8 attribution methods using the meta-rank benchmark is presented, generating a leaderboard that ranks the methods based on their performance metrics. The top 3 methods, input circled dot operator gradient, integrated gradients, and deep lift, exhibit more positive performance, while the remaining 5 methods perform negatively. Here is a combined summary of pages 13 to 16. The evaluation consistency of attribution-based explanations is presented in Table 4, with input circled dot operator gradient emerging as the top-performing approach and deconvolution exhibiting the poorest performance. The superior performance of input circled dot operator gradient is attributed to its ability to produce stable attributions in the face of perturbations by elementwise multiplying gradients with inputs. Integrated gradients ranks second, closely approaching the top-ranked method. Meta-rank provides a comprehensive benchmark for attribution evaluation across diverse test cases, effectively addressing the issue of inconsistent performance across heterogeneous cases. The meta-rank score, which can assume both positive and negative values, furnishes a unique, consistent, and practical measure of attribution performance. The efficiency of meta-rank is evaluated by measuring the time consumption of the ranking fusion module, demonstrating acceptable computation times even with a substantial number of methods. The discussion section addresses the choice of faithfulness metric, highlighting its solidity and generality for benchmarking attribution methods. Additionally, the issue of missingness bias in feature ablation is recognized, and the scalability of meta-rank is demonstrated, allowing for the inclusion of new attribution methods and the expansion of test cases. The paper emphasizes the importance of understanding how deep neural networks make predictions and identifies various challenges in interpreting their decisions. It reviews popular attribution methods, including LRP, deep lift, and SHAP, which aim to assign important scores to input features based on their contribution to the model's output. However, it points out that these methods often produce inconsistent results, making it difficult to trust their explanations. The authors propose a framework for evaluating the consistency of attribution-based explanations, considering both local and global consistency, as well as the model's performance on unseen data. The paper highlights the importance of evaluating the consistency of attribution-based explanations in deep neural networks, emphasizing that current methods relying on visual inspection or human judgments are subjective and may not accurately reflect model performance. To address this, the authors propose a systematic evaluation strategy focusing on 3 key aspects: model sensitivity, input sensitivity, and feature importance. This approach is demonstrated to be effective by applying it to state-of-the-art attribution methods and comparing results with existing evaluation metrics. The paper reviews various attribution methods, including gradient-based localization, input feature importance, and visual explanations from deep networks, discussing their strengths and limitations. The challenges in evaluating their performance are also highlighted. Notably, the authors emphasize the importance of considering both local and global explanations when evaluating attribution methods, as local explanations focus on individual instances, while global explanations provide insights into the model's behavior across the entire dataset. A balanced approach considering both types of explanations can lead to a more comprehensive understanding of the model's decision-making process. The proposed evaluation strategy addresses the limitations of current methods, providing a comprehensive framework for assessing the consistency and effectiveness of attribution methods. This systematic evaluation is crucial for understanding how well deep neural networks explain their predictions, ultimately leading to more trustworthy and reliable models.